Hello, welcome to this class. And here we go. We're starting with chapter one. So, definition of chemistry. It kind of makes sense that this is a chemistry class. We should talk about what chemistry is. It comes in a future slide, but chemistry definition is the study of matter and how matter changes, or how matter doesn't change. So we'll talk a little bit what matter is and and how it behaves. So matter, what is matter? Matter is anything that has mass and volume. So that's a definition of matter. And mass is how much matter you have, and volume is how much space that matter takes up. There are things that have volume but no mass. So energy and light, for instance, is an example of that. But matter, for what we're going to talk about in this class, there are some more exotic forms of matter, but we're going to talk mostly about atoms and molecules. And chemistry, very specifically, is how the atoms and molecules interchange and interact. So atoms, these are the building blocks of matter. So it's actually the Greeks that came up with this idea. Of course, they thought that atoms were tiny, indestructible spheres, but those turn out to be wrong. But so atoms are very, very, very small, and we'll get into the numbers of this, but they are very, very tiny. In fact, we can't even see them with normal light. So depending on the wavelength of light, but you can fit several hundred atoms along a single wavelength of light, for instance. So what are difference between atom and molecules? So a molecule is known as a stable group of atoms. So stable means that they actually kind of hang out together. Like think about a couple, right? What's a stable couple? What's an unstable couple? A stable couple is one that stays together, and an unstable couple is one that blows up, right? So fights and blows up. So what's a stable molecule? It's one that stays together. What's an unstable molecule? Quite literally one that blows up. So they don't stick around. Over here in this picture, we have a water molecule, for instance, and the water molecule has two hydrogen atoms and one oxygen atom. So looking at the image there. So generally speaking, water is a liquid, and we'll talk about that in a little bit. But basically, states of matter, solids have set shapes and volumes. Liquids have set volumes, but not set shapes. Gases neither have set shape nor volumes. So generally speaking, though, at the temperature and pressure that I'm currently at, and water, generally speaking, is a liquid. We humans can't survive in the environment where water would be a vapor. We can survive where water can become a solid. That is also known as freezing. But in Hawaii, where I am recording this video, it is very rare that we get to that temperature here. So water also is a unique molecule. One of the things that makes it unique is the fact that it tends to be a liquid over a long range of temperatures, especially for a molecule of its size. So it's only three atoms as far as molecules, and that's pretty tiny. So there are many, many huge molecules, and typically contain much more than three atoms. So it's an interesting molecule. So we talk about chemistry. Let's talk about chemicals. So this is something that kind of irks chemists sometimes. Like it's chemical free. Like what is that? Anything made of atoms is made of chemicals. Everything in touch, feel, taste, hold, that's made of chemicals. So chemicals pretty much make up everything. I mean, we say made of atoms. There are some things not made of chemicals, right? So light and energy are not chemicals. They're actually energy. And there are some exotic forms of matter like neutrinos that are not chemicals, but really everything else is. So we usually think of the word chemical as kind of having a negative connotation. So that it's a very general rule as far as what a chemical is. So it can encompass dangerous things, but just saying that something's a chemical doesn't mean that much. So, but chemicals are other things. So the air we breathe, air is actually made of matter. So you can wave your arms in the air and you can feel the air move. Air is a gas, and it's made mostly of nitrogen atoms, a little bit of oxygen, a little bit of water, argon, carbon dioxide, and other trace materials. So water is a chemical. So toothpaste, this is also a chemical, or it's made of chemicals. So it's not just a one thing. So water is a compound, and we'll talk about mixtures in a future class. But toothpaste is a mixture. As well, Tylenol, the molecule acetaminophen, that's the active ingredient in Tylenol. Tylenol typically has other stuff in there too, but Tylenol is another chemical. Toilet paper, yeah, we're really going for it with Pearson here. Yeah, way to go. Toilet paper, another chemical. So chemistry is the study of matter and its changes, and chemistry helps us explain why things happen, why things react, why things don't react, and these sort of things. So this is the realm of chemistry. Chemistry is all about the study of matter. There's other types of sciences. There's physics, which studies the physical world. There's biology, studies life. There is oceanography, studies the ocean. So various different fields. The kind of the three most broad sciences are chemistry, physics, and biology. And chemistry's realm is matter. So chemistry, we're going to talk a lot about matter here. So how are we going to look at the world? Chemistry is sometimes referred to as essential science. Because studying matter, matter at least is a center for many things. You can't have biology without matter. Although you could argue that chemistry is a subset of physics, but there is kind of a different way of approaching physics and chemistry. So, but as far as natural sciences, we use a scientific method. And the scientific method, and it's a way of doing things. So if you hear someone say it's a science, you probably should talk. What is the definition of science? A science is a systematic approach to solving problems. So if you say someone has a science, it says you are doing something systematically. And the method that we use specifically in science is the scientific method, and this is in contrast to some of the classical and neoclassical. We're going to say the ways that we look there. We look at reason, and you can see various types of reason. One of them is Platonic reasoning, and that's where you thought there was like a literal perfect thing, and you compare it to the perfect thing in heaven. So that's kind of the Platonic way of seeing things, and so whenever you hear the word Platonic, that's usually what you refer to that as having something compared to an ideal in heaven, for instance. But that's in the realm of philosophy. Here in science, we follow the scientific method. So here are the general ideas of the scientific method, and we have observations. Observations can either be quantitative or qualitative. So quantitative means quantity, qualitative means idea. A hypothesis is an educated guess. So we make an explanation, and you see the word tentative. So science is always tentative. So science is always on the verge of being disproven. So, and once science is disproven, you have to change the science, or the science is no longer valid. So then a scientific law, if you hear things like words like law of gravity, the law of gravity is what goes up must come down. You summarize large amounts of observations into one scientific law. And laws can also be equations. So it can be like Newton's second law, force equals mass times acceleration. That is Newton's second law, for instance. It can be an equation, or it can be a statement. So law of gravity. You can break scientific laws. So law of gravity can be broken. There's a law of conservation of mass, law of conservation of energy. You can break those too. So just because it's scientific law doesn't mean it's completely infallible. There are exceptions to things, but we have to understand how to explain the exception. So, for instance, conservation of mass can be broken, but matter and energy are interchangeable by approximately E equals mc squared. So we know about that. And that's an example how law of conservation of mass and law of conservation of energy can be broken. So that's one thing with science, is that we have to be able to explain around when our scientific laws are broken. And then the theory is a proven fact. A theory is a hypothesis that is supported by observations and experimentation, and it gives a more generalized idea. So atomic theory, for instance, is a generalized theory, that the fact that most matter is made of atoms, kind of thing. And germ theory is another one, that disease is caused by pathogens. Are all diseases caused by pathogens? No. There's many forms of cancer are not caused by pathogens. You could argue some are, but generally speaking, cancer is a disease that is not caused by pathogens. Cardiovascular disease is another one that is not necessarily caused by pathogens. It might be caused by pathogens, but it depends. Generally speaking, it's not. So that's what I mean, is that with science, we have these general rules, but we also have to be able to explain them. And if we can't explain them, then the theory is not valid. And there are very powerful theories that work very, very well, but are fundamentally false. So we'd use some of them in the class. For instance, Lewis theory, for instance, is a theory that's wrong, but we still use it because it works very, very well. So scientific method. So observation. Let's start with the observation. And this is something we observe. And we, of course, are talking quite a bit about sight, things that we can see. But there are other experiments. You can use other types of ways of observing things. We can certainly use instrumentation. So we can take like the weight of something. That's something you use instrumentation for. Okay, so moving on. After observations, we come up with a hypothesis. And generally speaking, good hypotheses are falsifiable. So they are falsifiable, meaning you can prove them wrong. So having a hypothesis that you cannot prove wrong is not a good scientific hypothesis, because how can you really, if you can't prove it's wrong, then how do you go back to if science is tentative or not? So, and we test hypotheses by experimentation, and then these either validate or invalidate the hypothesis. If your hypothesis is invalidated, you have to generate a new hypothesis. So that will explain why the experiment didn't work. So this is a continuation of the previous slide, and I've already kind of gone through all these. So this is just a scientific method. So experiments. So we test hypotheses or laws, and we see how they work. If enough of these come together, we can verify the law or the theory, or tweak the law or the theory. But if the hypotheses, laws, or theories, they are not confirmed by experimentation, then they have to change. That's the idea of science being falsifiable. And science is always evolving. And we can just revise our understanding, for instance. I mean, so as of 2024, as I'm recording this video, there's the Nobel Prize was released on mRNA and microRNA and how that works with gene activation. So that's not destroying our previous idea of protein synthesis in biology. It's just expanding upon it. But we've learned something new. So we've expanded our theory and understanding. So let's look at this image here for an overview. So I know it says a starting point, but I'll start with observations. Observations can either be quantitative or qualitative, and they come and they form a hypothesis, and then we test the hypothesis with experiments, and then if we get enough experiments supporting the hypothesis, we can use that to form a theory. And once we form a theory, we can continue to revise the theory to improve our understanding, or we can disprove the theory and the theory goes away. So many theories have gone away. And even though I mentioned that even if they are incorrect, they can still be useful. So we don't always just get rid of theories. We just kind of understand that it's not really how it works. Uh, Also, there's the more direct method. You can sum up the observations to form a law, and then you can tweak the law. So, for instance, how the law of conservation of matter, law of conservation of energy, can be broken. And through our, we know then that it's approximately E equals mc squared. That's not an exact number. That's an approximation actually for matter and energy. That's an example, for instance, how laws can be revised. So let's talk about scientific method, and I really like this guy, Antoine Lavoisier. So some history, like he was a French aristocracy, and so science for a while kind of used to be like the upper class were the ones that did science, and so many of the earlier scientists. So Darwin is another one, just a very rich aristocrat, and also some of the at least in Western civilization, the Catholic Church, a lot of times the clergy were also scientists, that kind of thing. So and Lavoisier, some stories about him. He, for instance, he would just drink milk. For instance, he wanted to see if he could survive just drinking milk, and that was one of his hypotheses, and he was seeing that. And he actually he met and fell in love with his wife, and this is what they did for fun. They would do different physical and chemical processes, and they found out that as long as they were very careful, they found that that matter was conserved. So there's his wife, an image there. They did that. I mean, so even they say it's all him. It was him and his wife. They worked together, and so this is in contrast to the Greeks. So the Greeks also believed in atoms, but instead of the 118 elements that we know of right now, they believed in four: earth, wind, fire, water. And they thought that earth and water were sort of like positive gravity, and fire and air were sort of anti-gravity. And they were really confused, the Greeks were, because if you took a piece of wood and you burned it, when you burned it, it would release all the fire, and it wouldn't burn anymore, and you're left with ash. And then you could take a metal like mercury or iron or something. If you heat iron up enough, it burns, turns to rust. Heat mercury enough, it burns, turns to mercury oxide. And they were confused because when you burned metals, they got heavier, but when you burned wood, it got lighter. And so they're trying to figure out what was going on there, and they couldn't quite explain it away. Of course, we can explain it away now using atomic theory, but that's something that really bothered the Greeks. But what Lavoisier would do would burn things in closed systems, capture the carbon dioxide, capture the water in the combustion, and if the two pairs of the Lavoisiers were very, very careful, matter was conserved. So the Lavoisiers, they don't credit his wife. I would like to credit his wife. Together, they have the law of conservation of mass. In chemical reactions, matter is neither created nor destroyed. So, I mean, it also includes chemical processes like melting and evaporation. But this shows the power of a law. He took all of his experiments, well, their experiments, the husband and wife, and now can predict future ones. So atomic theory. So atomic theory is very central to this class, and the idea is that matter was made of atoms. So this was a really hard sell. I mean, this is something that we were not entirely sure of for a while, but now we can see atoms. And if you look at that image to the right there, that is a scanning tunneling microscope image, and you can see like the image of the atoms, and the first thing you want to say is this looks kind of weird. The atoms, if you look on the surface, they look more like pimples, and the reason for that is because the way that the STM scanning tunneling microscope works is that it takes a piece of tungsten and moves it across the surface. You apply a current to it, and what you're seeing is where the current is and where the current isn't. So when you approach a spherical atom on the surface of whatever it is you're looking at, you start to get an image of the atom. You get the presence of the electron cloud a little further away from the side of the tip. You get a strong signal on top, and then as you move further away, you get less of a signal, and that's the reason why they look like pimples. So that's why they don't necessarily look like spheres. It's the nature of the experiment, just so you know. So and this image here specifically is cobalt atoms arranged on a copper surface, and this is really hard to do. This is very difficult to do to move the atoms and put them in the right spot. Not only that, to image them. I'm not an expert in this, but I've had friends that have done this, and it's really hard to get atomic level of precision on this. There's not always atomic level of precision. So this is a hard image to make, and this is a hard thing to make, to literally push atoms around and to do. It can be done. I mean, obviously we did it, but it's difficult to do. So, but we have this image, so now we know it's real. But I mean, before this, this is a hard sell, and we'll talk about this in future lectures. So let's talk about this a little bit more. Let's define these as observation, law, or theory. So A, when metal is burned, the mass of its contents does not change. That's an observation. So we are observing something, and okay, so B, matter is made of atoms. So this is a theory. This is atomic theory specifically. So then matter is conserved in chemical reactions. This is a summary of observations. This is a scientific law. And then D, when wood is burned in a closed container, its mass does not change. This is an experiment, but you could also, for these, it's an observation. So we've taken data from an experiment, and this is the observation and the result of that experiment. So we observe certain things. So these observations, and so what our observations are referred to are data. So one thing to note, the word data is plural. Okay, so the data are. You don't say the data is. An individual, and we even say the word data point, the technical term is datum. Datum is individual. Data is plural. And it's very rare that we're talking about a single datum. We usually talk about data. So with that, be careful with when you write things, always say plural when it comes to data. So the rules of English or whatever language you're using is plural for data. So let's look at these data here. So mass of water sample is A, B, and C, and you have different masses, and you have the different amounts of hydrogen and then the different masses of oxygen. You might not see this starting off, but we'll talk about this in the future, but you might notice, if you can do the math in your head, there's the same ratio. So this, you can also take these data and partially show the law of set proportions. So law of definite proportions. So this is an example of the law of definite proportions. But you can see, that's an analysis of those data right there. This conforms to the law of definite proportions. So what's the pattern? Well, hopefully you can start to do that. So already, I mean, as a chemist, I kind of looked at that. I'm like, oh yeah, definite proportions. So we can also do things and plot things to have graphs and images. So down here, for instance, you see a plot, and you have the x-axis and the y-axis. So typically speaking, the x-axis, this is known as the independent variable, and the y-axis is the dependent variable. So that works for all mathematics, for all things. You can even have multiple axes. You can have a z-axis or z if you're in Canada or UK. So you can have more than multivariable dependencies. For instance, we'll mostly do 2 dimensions, so x and y, but you can have multiple. But the y-axis depends on the x-axis, and the x-axis is the year, and then the concentration of carbon dioxide depends on the year. And you can also see with the chart that they move the chart up. The origin of the chart is, it looks like the zero would be actually 317 parts per million. That's an example of how you can change the offset of the graph to make that. So, but looking at these data and trying to figure out what this is, and you say, well, obviously there is a relationship between the year and the concentration of carbon dioxide, and the most obvious answer is it appears to be going up, but also after the year 1960, it seems like the relationship changes a little bit. So that's something you could look at these graphs and say something with that. So what does this tell you? So I kind of already gone over that and explained that a bit. So just moving on with that. So now you yourself are beginning as a chemist. This is a prep class. So how to succeed. So for me personally, I've always been a why child, and that's part of the reason why I went into chemistry. So so think about things. So this is, I mean, truth be told, this is the stuff we talk about in this class. If you're like, why did someone, why did I dedicate so many years of my life to balancing chemical equations? That's not the fun part of chemistry. The fun part of chemistry is explaining why. I mean, the chemical arithmetic and solving equations, that's just part of the chemical language. It's just something you have to know how to do. But the fun part of chemistry is explaining why things behave the way they do, or even also how can we use this stuff and apply it into other things. So what kind of laundry detergent should I use? Can I put bleach on my colored clothes? Well, it depends. It depends on what they're made of. So for instance, I can put bleach on my colored polyvinyl chloride dry fit clothes and not stain them. But if I put them on my colored cotton clothes, it will stain them. So these are some things that you can do as a chemist and understand. So with this, though, as I mentioned before, even though the fun part of chemistry is the understanding, it requires calculation. So this is a math-based class, and we're going to do quite a bit of that. And many things involve quantification. So the word quantity means numbers. So there's going to be a lot of numbers in this class, and a lot of numbers, a lot of math. So we need that. And we also need to be able to look at things and also get data on them that have more precise measurements. So, for instance, if I put my hand into water, I'm kind of, maybe I'll get a general idea of how hot the water is, but a thermometer is going to be able to do a much better job than me as a human. Of course, a thermometer is also going to be able to handle ranges that I can't. So, I mean, I do not want to put my hand in 100-degree Celsius water that's boiling, so that's going to hurt, for instance. So, also, chemistry, a lot of people have a hard time with this class. I of course, love it, but I mean, it's easy to make small mistakes. And so, of course, this is a system. So chemistry is a system. It's a science. It's a system. So look at the system, try and understand the system. And once you get a hang of it, it becomes a lot easier. And quite a bit of what we'll do in this class is dimensional analysis. So it's not for everything, but it's a strong thing we'll talk about in future lectures. So about this text, so if you're going through the textbook, these are some things you can expect with them. And here is the last slide for the chapter. And thank you, and I will see you in the next chapter.